this is week 9, the first lecture, which will follow up the capacitor and capacitance. This lecture will round up the 3 lectures about electricity. And next lecture, we're going to look at thermophysics. We also have 3 lectures on thermophysics. In week 11, I'm going to give you a revision. So this is the plan of this course, all right? So before we look at capacitor or capacitance, I just give you some review on one of the most important electrical component, which is resistor. Now, you know, first, the symbol for resistor is this one or this. They're equivalent. Now, a resistor, as the name suggests, it resists the current. So let's look at how we define resistor. We say the resistor R is V over I. Now, what it really means, if you imagine you have a battery here, you have a resistor. Now you can change the voltage. So you measure the voltage across, and you measure the current through the resistor. Now, if you say you want to have 1 ampere of current through this resistor, how much voltage you have to set? If you say, I need to set only 1 volt, such that 1 current of ampere, 1 ampere of current will pass through the resistor. I say the resistance is 1 volt per ampere. It means 1 ohm. Now, if you have another resistor, which it require for the 1 ampere require 2 volt, so it means the other resistor, the second one, will have higher resistance. It just means 2 ohm. So you see the meaning of ohm. It means how much voltage potential difference across the resistor. In such a way, you can push 1 ampere current through the resistor. The higher the voltage, it means you need more energy to push it through. It means the resistor is higher. So this is the physical meaning of resistors. Make sense? Now, we have another device. This time we are not talking about current. We are talking about charge. So this is the capacitor. Now let's look at how physically a capacitor can be made. Again, before we look at the capacitor, we look at, again, the resistors. Now, yes, once you have, usually it's another way around. You have to find the material, say 2 ohm. You have to find the material which, or a resistor, which gives you 2 ohm. Once this is determined, the voltage and the ampere, they are connected. It means if you put 1 ampere, you need 2 volts. If you want to pass through 2 ampere, you need 4 volts. So this is the one predetermined. Now, what determines the resistor is the properties. So the resistor is determined by the length of your wire, the cross-sectional area of your wire, and proportional to the material probabilities, the properties. So R is proportional to L over A. So we call this one resistivity, which is the materials dependence. This is geometry, the external dimension. So this is all about resistors. So you can make a resistor which according to the requirement in your circuit design. Now let's look at capacitor. A capacitor is simple. It just have 2 metal plates. There will be a gap here. It means they're not connected. Make sure there's no connectivity between the 2 metal plates. Now this gap, it can be vacuum. It can be air, or it can be any insulator. Now in this stage, we'll assume vacuum and air. They're similar, very close, but at this stage, and later we'll look at, instead of air or a vacuum, if we put a insulator in between, what happened? Okay, so because this is metal, you can connect this one with a battery source. So in reality, you know, is the electron will start from the negative side all the way here. So the negative plate will start accumulating electrons. Now, this electron here accumulate here on one side, the flow of electron. It will repel electron of the other side too. So if one stay here, you got another electron repel. Now remember, it's because the induction. It's not because it's really physically connected. So one electron, you repel one electron. So yes, there will be a current, but this current will not last forever. Just like it won't like resistor. You can keep putting current in until your battery flat. So what happened is, yes, initially you got some current, you got some electron accumulating here, but eventually it will produce its own voltage. This voltage will try to opposite further electron come. It means eventually you will build up voltage across this plate. And this voltage will be opposite to the external source. Eventually, no more current, and the charge within the two plates become a constant. And this constant charge is the maximum charge it will hold, the Q. Now, it also, as I say, will develop its own voltage. This voltage, if you got a 9 volt, he will develop another 9 volt. So what it means is, as if in the beginning you have a 9 volt, as if in the beginning the current will flow, but after you build up the negative here, the positive here, you see it's a little bit like you connect the two battery. Can you see it? This is also positive and positive, so they're opposite each other. Therefore, there's a no current here. Now, this voltage, of course, will, if you got a 9 volt, this is also 9 volt. So this voltage is equal, opposite to the external one. So therefore, you have a voltage, you store charge. So we define a quantity called capacitance. A capacitor means if you have a 1 voltage, how much charge you store. If you can store in one voltage, you get 2 coulomb of charge. We say this 2 Faraday. So Faraday means coulomb per voltage. It's a big unit. You usually won't see 1 or 2 Faraday. Most likely you will see microfarad, nanofarad, millifarad, or picofarad. So sometimes, I mean, we so-called the supercap, we can have sort of Faraday, quite big, but usually in the old day especially. All right, this is the idea. Now, once you got a charge built up in between the two metal plates, you got electric field. So remember, we learned this one in the last lecture last week. The electric field here is equal to, the field strength is equal to negative delta V delta X. If we say this is your X, or if you say this is your D, it doesn't matter X or D. It just means the separation between the two plates. So it's the voltage over the separation. You got the electric field. All right. So what really happens is, usually we have just a metal plate. We keep this one in vacuum or in air. In reality, what you do is you put the two metal plates and you insert a piece of paper here. It could be paper, it could be any other insulator. So just as long as you make sure the two metal plates, they won't contact or in physical contact. Now you start roll, just like a toilet roll or your rolling, yeah, whatever roll you want. So you roll your metal and insulator. Now this will create a lot of space and also will create a lot of surface area. Because remember, later we'll come back to what determined the capacitance. Now let's look at one important thing is, again, what is the electric field create here? I say the electric field in between is delta V delta X. Another expression is permittivity of free space, the charge density, all right? And this is, okay, over. So it's the surface charge density over the permittivity of free space. Now, therefore, we have two. The first of all, how to find the surface density, surface charge density. So to find it, you have to know the area, of course, and you have to know what's the total Q. So we really want is the total Q over A. So we want the A, we want the total Q. From here, we know the electric field. So if you look at the electric field here from these two expressions, we say electric field is equal to sigma over epsilon, and sigma is Q over A epsilon, and therefore charge is epsilon A E, just like here. Remember, capacitance is Q over V. At the same time, E is equal to V over D. The D is the separation. So we can put the E back, put the E. So we can say, okay, Q is epsilon A V over D. All right, so Q over V is epsilon A over D. And remember, Q over E is your capacitance. So we have two expressions, this one and this one. This is similar. This is similar to resistors. Resistance, remember I say, is V over I. Each current, how much resist potential you require to push it through. How to make this one is this one. So this part here is similar to this part. So this is how the manufacturer, how can you make the capacitance from A, choose the area A, and the separation D. Now, before you put anything in between, there's no material dependence. So this is all you need. You can control. You can make your own capacitance just by choosing the right area and the gap between. This is your real capacitor. Your real capacitor is always have a in between. This is insulator. And if they usually put some oil in between, and this oil is important to make sure you have a good surface contact and insulation. And it's quite messy, so people usually don't open this one. So make sure you don't open it. And also this type, there's at least two types of capacitors. The first one is electrolyte, which you have different positive, negative. You must follow which side is positive, which side is negative. The other two is ceramic. which is there's a no polarity. That's just you can connect your resistor or capacitor whatever side. Okay, circuit diagram. How we know resistors is represented by this or this. In capacitor, it's represented by just two lines. They are equal length. So don't confuse these two. This is battery. This is capacitor. All right, some rule. Just like resistors, we want to sometimes we have 2 or 3 capacitors connected either in parallel or in series. You want to find their equivalent. It means you want to replace many by one. Now, when the capacitor get connected in parallel, the rule is just add the capacitance. So this is important. A little bit like you connect the 2 resistors. Remember R1, R2, when you connect them in series, you add. So this one is R1 plus R2. You add. Now, this time is different. When the 2 capacitors, they connected in parallel, you add. The reason is simple, because you're adding more surface area. Can you see it? They're parallel. So it means you more surface area. Therefore, the capacitor with proportional capacitance is proportional to the surface area. So you increase the surface area, you increase the capacitance linearly. So you double the surface area, you double the capacitance. What's the difference? Another thing is the voltage. This is V. If this is V, this is V. This is also V. But how much charge stored in this plate, they are different. Remember, C is equal to Q over V. So another way to rewrite this expression, the definition, is the Q you store is capacitance multiplied V. Now, they have the same V, but different capacitance. So therefore, the Q1 here is C1V. The Q2, C2V. V is the same, but C1 and C2, they may or may not be the same. So Q1 and Q2, they may or may not be the same. So it just depends on the capacitance. All right, in parallel, I beg your pardon, this is in series. Can you change it? Yeah, this is in series. If you have 2 capacitors, if you connect them in series, what happens is, now let's look at how those charges will build up. You see this diagram here. If you have negative here, so that the electrons start coming to here, imagine you build up 2 negative charge on one side. Now, because induction, if this side, just like a river, this is vacuum, you have 2 negative charge. You also find you have 2 positive charge opposite side standing in, just like river. 2 negative make 2 positive. Now, this 2 positive charge, why here? Because it drives the 2 negative out from here. These 2 negative come to here, of course, will stay. They cannot pass through. They will just stay. So you see, if you have a 2 negative, you have a 2 positive opposite. If you have 2 positive opposite, you also have a 2 negative on the other capacitor. This 2 negative, of course, induce another 2 positive. So overall, if you have, say, 2 nanocoulomb of charge on the other side negative, you also have 2 nanocoulomb positive charge. You also expect 2 nanocoulomb negative charge. And you also have 2 nanocoulomb positive charge. They're all same. Can you see it? So therefore, if you connect the capacitor in series, this time they don't have the same voltage, but they have the same charge. So this is important. So how about the voltage here? V1, of course, remember again, C is Q over V, V is Q over C. All right, so it's Q1 over C1. The V here, V2 is Q2, Q2 over C2. Now Q1 and Q2 the same. Q1, Q2 the same. So you expect you have a same different voltage. All right, how to find the equivalent? The equivalent is 1 over. So this is a little bit like resistor in parallel. Can you see it? So this is all you need to remember. Now I think I have to move a little bit fast. My Apple Pen have a problem. Only about 5%. I hope to finish. All right. I know the new generation of iPad Pro, you can charge this one automatically. So I don't need to worry every time sometime, oh, I forgot to charge it and cause these problems. I skipped this one, so it's so easy. So can you look at this example and see which one has a higher capacitance? Now we assume, let's just do the first one for you, C. If you have this one, what it means, they're parallel, they're series. So CS, 1 over C, 1 over C, 1 over C. So it's a 3 over C. So the overall, the equivalent is 1/3 of this one. All right. How about the second one? The C parallel, of course, C plus C plus C. So you got 3C. How about the third one, number C? Now, can you do the C and D now? C and D. Now, the idea is just like resistor circuit. You first try to solve this one. In D, you try to work out this one first. And then you use another rule. So can you do it now? A little bit like resistors. They're all C. They're all C. So in terms of C, they're all same value. So just like here, the first A is 1/3 of the C. B is 3 times of the C. How about C and D? Yeah, let's look at it. Now, you have a 2 capacitor here. So they're connected in parallel. So this becomes 2C. Now this you connected in series. So 1 over CS. The overall is 1 over C plus 1 over 2C. Now you find the common denominator. This is 2 plus 1. So 1 over CS is 3 over 2C. And CS is 2 over 3C. Got it? Now how about this one? Now again, you first find, now usually it's easy. If you have a 2 with capacitor that's the same value, they are connected in series, you just half them. It's because I can show you why. Series, C. So here, just like here, you connected 3 in series. It's 1/3. If half, C over 2, 1 over CS. So CS is C over 2. So it's a half. So this one here is C, and this one is half C. Now they are connected in parallel. So the parallel circuit is C plus 1C over 2. So you got 3 over 2C. Okay, which one has the highest has the highest capacitance? B. And next one is D. The one is C, and then A. Energy. Now, the whole idea of capacitor is store energy. Why you store energy? When you bring the two positive charge and negative charge together, energy is stored. Now, we discussed this a little bit last time. So I want to recap a little bit the idea why energy is stored when you have a two charge opposite each other. Remember I say when you drop this thing, it just, when I release my finger, it just dropped. Now you can say because the gravitational force. But another expression is, I say the potential energy is high. When I drop this one, it will go to the lower potential energy. Make sense? So this is, we explain the same phenomenon with the idea of energy. Now, think about if I put a positive charge in one side, negative charge in the other side. When I release my fingers, what happened? They come. So what I mean, you already got some energy here. Once they release, they will go to the lower energy. Make sense? So this must be high energy. This must be low energy. Just like I release this one, it goes to the lower energy side. So whenever the same idea is, whenever you release an object without any constraint, naturally the object will go from a high to low potential energy. Got it? So therefore, yes, when you keep charge opposite side, you already got energy here. If you really connect this one, the negative will go here, positive go here. It means just like they go from high to low energy. So it means you have energy stored in your capacitor. So a capacitor sometimes, just like you can think a capacitor, just like a power source, like a battery. But this time the battery is a little bit different. You cannot keep pumping charge or current. Now, if you plot V versus Q, now let's look at the dimension V, Q. If you have a rectangle here, what's the area of the rectangle? V multiply Q. All right, the value of V multiply the value of Q, so it's the area. Look at the unit. The V is joule per coulomb. Charge is coulomb. So when you look at the unit, what is the unit? Joule. So what it suggests to you? It suggests to you the area here is energy. Got it? Now this is important. Now we say the area under the V versus Q curve is energy. So if we look at how we do it, go back to definition C equal to Q over V. Now you rearrange your V is equal to 1 over C Q. Can you see it? Now if you just compare with y equal to mx. Now this is your y-axis. This is your x. So your slope is 1 over c. So if you plot v versus q, this is your strict line because 1 over c here. Now, but this time you're not interested in the slope. You're interested in the area. The area is once you store so many charge here at this position, how much energy you stored in this capacitor. Make sense now? Now, how to calculate the energy? Of course, the area is half VQ, all right? Because this is not a rectangle. This is a triangle. Now, this is what I say. I beg your pardon. This is U. This is energy, and the unit is joule. However, you know C is also, by definition, equal to this one. So the Q is C over CV. So you can substitute the Q by CV and become this expression. And you can substitute V by Q over C and become this expression. So the three expressions, this one, this one, and this one, they're equivalent. A little bit like, remember, a little bit like resistors. Remember, R is V over I. The power through the resistor is IV. Why? Because I is coulomb per second and voltage is joule per coulomb. So you got joule per second. This is watt. Now we also have the same, because the Ohm's law, I square R and V square over R. So the three expressions, they are the same. Just like here, the three expressions. But this one is for power. This is for joule per second. This one is just for joule. It makes sense because capacitor, they just store energy. You're not talking about energy per second. So it's how much energy you store. So it doesn't have time, this idea. Is it clear now? So how do you compare the three expressions? Now, this is repeat. Now, when you put the, we call insulator. Now, sometimes we call this dielectrics. It actually interesting. Now, a dielectric, it means because you have an electric field. So if this atom is neutral, you will drag those positive and distort your atom a little bit. Now this is why we say if you have a neutral atom, this atom will become a slightly distort under the influence of external electric field, become negative and positive. We call this one dipole. And we call this one induced dipole. It means originally you don't have dipole, but it induced by the external electric field. Another type of dipole is called permanent dipole. It means the molecule itself is a dipole. One example I used before is H2O. Oxygen here, hydrogen, hydrogen. We know they share a pair of electron, but oxygen have a higher ability to drag the electron close to the oxygen. So you expect the two share the pair of electron that close to the oxygen side. Therefore, this is delta negative. This is delta positive, delta positive. So the water itself is a permanent dipole. And I said before, this is an important properties because it is the permanent dipole make a water have a very interesting physical properties and chemical properties. And from there, it also make life possible. E reduce. Now remember, E is equal to delta V delta X. So when E reduce, why E will reduce? Because you see these figures. When you have a dipole, the dipole will create its own electric field. But this time, the electric field created by the dipole is opposite to the external. So overall, you reduce the electric field inside this plate. So therefore, if you look at the relationship, when E field reduce, the voltage also reduce. But you see how capacitance defined. The capacitance is defined by Q over V. You still hold the same charge, but now you can hold the same charge with a lower voltage. So the V reduces implies C increases. It means now you can hold per unit voltage. You can hold. All right, so you got a permanent dipole or induced dipole. Whatever dipole you have, you reduce the electric field between the two plates. Electric field reduced, the voltage reduced, but you're holding the same charge. Therefore, the capacitance increases. Now, how can we capture this phenomenon? The capacitance increases when you insert any insulator in between. The idea is we say the C is equal to Kc naught. Naught is the capacitance in vacuum. Once you insert something, you guarantee the capacitance increases. So the K will be bigger than 1. Let's look at some value of K. And we call this one dielectric constant. Kappa actually is a Greek letter. Vacuum is 1. So yes, for sure, because this is vacuum. So the C is equal to 1 multiplied by C vacuum. Air, you see air is close to 1. It's 1.00058. So the air increased a little bit, not much. Teflon is 2.1. Polystyrene 2.6. Nylon 3.4. Paper 3.7. Glass 5.6. And some oxide even up to 26. Water 80. Strontium titanate 256. Now this all number is important because when we try to squeeze our circuit into small integrated circuit IC chips, capacitor is one of the components need to squeeze into small nano size. But if the area becomes so small, you have to make a gap small, but at the same time, you also want to find the material insert which produce the high capacitance. Another column here, you see, can you see what this means? Is the maximum voltage, maximum electric field, or course mean voltage. Now what it means, explain a little bit here. Now yes, you put dielectric constant here, you put some, but if you keep increasing the voltage, so it means the external electric field keep increasing. You keep putting more electric field here, stronger and stronger. What happens is this electric field will eventually drag this positive away from the negative. Can you see it? So the positive charge will go this way. The negative charge will go this way. We call this one dielectric. The insulator we call dielectric breaks down. It breaks down. So it means the molecule just tear apart by the electric field. And those positive ions will go to the negative side and you create a current. Now this happens not just for any material, including air. That's what lightning means. Later we'll look at the slide. So there's a maximum electric field you are allowed to supply. It means, remember, E is delta V, delta X. So there's a maximum here for a specific X. There's a maximum voltage you can put. You can put across. Once you over this voltage, you will break down. You will cause trouble, and this breakdown usually is irreversible. It means once it breaks down, that's it. It damages everything. So you cannot use this capacitor to store energy anymore. Therefore, the electric field, remember, because it's delta V, delta X, so it's volt per meter. Now this is a megavolt per meter. You see, vacuum is infinitive because this is vacuum. Air is 3.0. So each one have a different value of dielectric. Water depends on the purity. All right, so this is how this idea, this mathematics, it means after you insert a material, your capacitor, it increases and multiply a dielectric constant. Dielectric strength, we just look at it. This is exactly what lightning means. Lightning is dielectric breakdowns. It means the electric field is so strong here. It breaks down the air molecule. So the air molecule, once say nitrogen, it breaks down nitrogen 2. One becomes nitrogen negative, one is nitrogen positive. The negative side go here, positive side go up. So this is a flow of electrons. Sometimes it's the electrons. So it can be a mix of electron and ions. This is striking, beautiful image of lightning. Capacitant and dielectric. The capacitance can be stored, can increases. This is how it increases. You see the K here. So that it just means, remember, capacitance is so this is not a vacuum. Zero mean vacuum. Now once you put dielectric constant, the dielectric constant here, some people will rewrite this one, but don't worry about it. Some will do it. Energy store. Now I'm not going through the detail. I just want to warn you, interestingly, once you put dielectric material inside, the energy actually drop. Okay, how much you can store? So you store less energy, but higher capacitance. One example is important is biological system. In our cell, the cell membrane itself is a capacitor. It's a capacitor. And you know, all this sodium, potassium, they are the one driving that. I mean, if you look at the nerve cell all between, I forgot all the I learned in biology. There's an electricity across, but the electricity is not just current or free electron. In biological system, we're all full of electricity inside, but they're not like a metal with free electron. They use ion. Most likely they use ion in the fluid. So yes, this time in the biological system, the ions, positive and negative, they do have positive negative flow. And you can build up across the membrane, the cell membrane, a capacitance here. And this capacitance can have a great influence on biology. So yes, it's a huge area. I mean, you see that's how we use the concept physics into biology, other field. RC circuit. Now we are going to look at details of transient event. It means we want to look at what happens when you just close the switch. Now usually we'll call this, there's two different configuration. We call this one charge up. R mean resistance, C mean capacitance. If you connect your resistor and capacitor in parallel, so when you close this one up, what happens is you want to look at Kirchhoff law. If you already in the tutorial, you remember. The potential here, the EMF, is equal to the drop IR and the drop V. Why this term? Because the voltage here, C over QV, so the voltage is Q over C. So you see Q over C here. So this term here, what happens is once you drop here, you do have a current. And this current will, as if C is connected. At the moment, when T just bigger than 0. So there's a big current because you come one negative, there's one positive, you're driving the electron through. So the initial current will be just like a simple resistor, V over R. But this current won't last forever. It will drop. Why? The more electron you stay here, it will repel more electron coming through. Just in a way, it's like a human being. So some people already stay a good place. They try to stop other people come, unfortunately. And yes, same happened for the electrons. So the electrons here try to stop further electron coming. So the I will drop. And how it drop? Exponentially. So this is how you will see here. At the instant when the switch is closed, okay, the battery potential is fixed. The capacitor is initially uncharged, so you don't have any voltage across it. So you got the initial current, which is V over R. As the time passes, you got more and more capacitance built up, more charge built up. This charge will stop further coming, so you reduce the current. Eventually, you got the same voltage. So you stop all the current, therefore it stops. So we put this one into a mathematics. Now this mathematics, I'm not going to prove it. I will let your math teacher do it. Now this is a differential equation. This is a solution of a differential equation. That's all I can say. Now, but let's look at the meaning of this solution. First, current, as I say, initially, you drop here, and then the current will drop. Now, when you look at how it dropped the current, how about we look at this first? The current drop, we call it exponential decay. Now just remind you exponential function, y equal to ex. How would you draw y equal to ex? This one, all right? So this is x, this is y, this is 1, of course, when x equal to 0. Now, how would you draw y equal to e minus x? This way. All right. So this is exponential decay. This is exponential growth. Now there's another important graph. Which is this side is we call exponential charge up or approach to a constant. This is how the voltage or the charge build up. Now all of this, if you look at the decay first, the current will exponential decay. Now one thing I want to draw your attention is different in engineering and physics and math. Math, most of the time you only do like this, agree? But here, these numbers should be dimensionless. Again, that's why we have to look at the dimension. So what it means is this is a number. In math, it just say x is a number. But in science, in engineering, you see T over RC. So this must be a number. It cannot carry any unit. If you look at this T over RC is a number, what it suggests to you? What is the unit of T? Second. So what is the unit of RC? It has to be second. It doesn't look like it is second. Now therefore we first prove this property here. RC, I want to prove is second, is a time. So the R here, all right, R is defined by V over I, all right? C is defined by what? Charge per voltage. So when you combine RC, so it's V over I, charge per V. So first the V cancelled, but Q over I. RC, the Q is coulomb. How about I? Coulomb per second. So therefore is second. Can you see it? Yes, RC is second. Now we call this one time constant. Now the idea of time constant is important. First of all, if you use your calculator, all of you, if you have your calculator, if you look at what happened is here. If you look at this exponential decay, if this is 1, if it decay as minus t over RC, if t equal to 1 RC, it means RC you can be predetermined RC value. And then if your time, the real time is equal to RC, what happens is E become minus 1. Can you do your calculator? Use your calculator. What number you get? Come on, please. If you don't, I can tell you 0.368, about 37%. What it means is when the time here is 1 RC, it will drop from the initial to 0.37 of initial value. So this is exponential decay. You may ask, how about the other RC, 2 RC? You will drop to 0.77 square. It means another drop. So this is what we look at, how exponential decay. If your exponential growth, not growth, approach to a constant, just like the voltage or charge build up in the capacitor when you charge up. When you got 1 RC, you got about 63%, okay, of the charge up. So here 2 RC, because 60% is 1 minus 37%. So how about here is 1 minus 0.37 square. So this is how you do it. All right, how you charge a capacitor. Now let's look at this example here. An RC circuit consists of 2.0 millifarad in series of, so this is 2.0, this one. So you got the 12 volt. After the switch is closed, what is the maximum value of the current? You know the current is look like this. The maximum value here is 12 over 6.4 kilo ohm. All right. So do I have the number here? Yep. So this one here is 1.88. 1.88. What's the maximum charge? The maximum, now if you look at how the charge build up across here, it's like here. So the maximum charge is the capacitance CQV. So the charge Q is CV. Therefore, it's CV 24 millicoulomb. All right. When the charge is half the maximum, now this is we call the half time. It's another concept. what is the charge, what is here the time when the charge is maximum, or what is the time when the current is half the original. Now do some mathematics. Please follow the mathematics. It's important because they're simple. They're so-called the concept of half-time concept in radioactivity decay the same. The potential here, or the charge, is VC. VC, you got half. So this is half. You cancel this one. You got half 1 minus E minus T over RC. We arrange this one. You got this one. You take that natural log. Now I do a little bit here. Half minus 1 is equal to minus. So E minus is half. So you take natural log. You take natural log. And this one is your minus T over RC. So you rearrange this one. This is a factor. Again, this is about 60. This logarithm half is about 69%. So this is your time, half time we call it. The time, which is usually less than RC, 69% of RC, will be your half time. All right, discharge. Yes, you can also discharge. Once you got the charge up, you can just close this one and let the capacitor like a battery. So the charge build up originally will just go through and cancel out each other, and the charge will discharge, and the current the same, drop exponentially. And the equation, of course, is simple for exponential decay, and same as the current. All right. So the initial current, again, I naught is the voltage initially over R. All right, this is your discharge circuit, and the voltage, of course, also drop. That's it, and we will stop here today.